right, we're going to take a look at how we can start doing calculus with a new kind of function that you haven't seen in a while, parametric functions. Just as a quick refresher from pre-calculus, usually we have what we call rectangular form. We plug in an x and we get out a y. We have a domain, which is all of the x values we can plug in, and whatever we're able to get out, we call range, those are the set of y values. So if we change that up to where x and y are their own functions, but then they have the same input, this is when we have parametric. So typically we're going to use t, but you could use anything you want to. T is called the parameter that x and y both depend on. Now since t is the input for both x and y, now the domain is the set of t values we can plug in, and your range is going to be the set of x and y values that you get as outputs. So if you were actually to graph, the range, it's going to be a region in the xy plane versus an interval on the y-axis. So for an example, let's say I have x and y here. X is 3t minus 1, y is the square root of t. And someone says, tell me the domain of the parametrically defined function. So looking at that top function x, we could really plug in anything we want to because that's a linear function, domain and range, all real numbers. For my y function, the domain is restricted. I need only only non-negative numbers. So I need my domain to be a set of t values that I can plug into both x and y. For that reason, I'm going to use t greater or equal to 0. Because even though x can take more inputs from t values, I need the t values to be plugged in simultaneously to the x and the y. I can't have some defined values for x and undefined values for y. They have to be points in the xy plane. I need an x paired up with the y. So how is the calculus going to get involved? So this is new stuff. Last few slides were a review from pre-calculus. Turns out that if I was to come up with a formula for the slope of a graph of a parametrically defined function, it comes out to be dy dt over dx dt. That means the derivative of y with respect to t, Leibniz notation, divided by derivative of x with respect to t. So going back to that same function, let's say someone tells you find the slope of the graph of the function defined by x and y when x is to 2. So we know dy dx is dy dt over dx dt. You can just use your derivative rules. I'll tell you one thing. Most people tend to say 3 over the derivative of t to the 1/2. Be really careful because it's dy dt over dx dt. So that should give us the following. -1 over 2 t to the 1/2, because using your power rule for the y function, and then the derivative of my x function is just a 3. Now we have an issue though, because it's asking for the slope when x equals 2, but here I don't have x, I have t. So typically what's going to happen with a lot of your derivative problems with parametric functions is you're going to typically have to solve for a t value or multiple t values. So what we're going to do is use the fact when x is 2, I can go to my function x, and then I could plug in a 2, and then solve for t. So if I do that, add a 1, divide by 3, looks like t is a 1. So then I can go back to my derivative formula, plug in a 1, and looks like I get 1/6, or -1/6. That'll actually do it for this video.